condition where we can use the law of sines to solve a triangle. And what we had seen so far in our first lesson, we had worked in a situation where we were given two angles and one side. And I'm just going to put this out here real quick. Just go ahead and fold paper. And just take a look at the top of the paper that I'll present here. Don't worry about anything else at the bottom. The case where I gave you two angles, and let's say it happened to be angle A and B in this particular example, and I gave you the length of side C. I've written the law of sines. I've starred what we have in red. So far, I have one piece of each ratio. Well, to be able to solve for all six values, the three that I need to still solve for that are unknown, I got to make one of these ratios complete. And the nice thing is, if I wind up with two angles, because we know the fact that the three angles of a triangle need to add up to 180 degrees, I can simply solve for angle C. 180 degrees minus angle B minus angle A, those two measures. Subtract them both from 180, and I'll know what the value of this third angle is. And as soon as I have three angles, plus gee whiz, I got the side that goes with this last piece, I know this ratio. And so now I have this piece. Go ahead and make it red. And now with four red pieces, I can do some very quick equalities. Sine B over B equals sine C over C. I know these two numbers now. I know that number. I can solve for B very quickly. And the same thing is true to solve for little a. So anytime I get two angles and a side, I am great to go with the law of sines. But now we're going to walk a different case. And this is the case where I have two sides and one angle. And it turns out that the angle is not in between two of the given sides. We're going to set this up. This is called the ambiguous case. And I'm going to describe it using the following story. We're going to demonstrate it using some Lego bricks. Here's how we set it up. You're going to start owning some property for which you need to build a triangular fence. You're going to start at your property in the left-hand corner of your property. This is kind of like the border of where your property is. And it turns out that right at that border, running along to the east or to the right, whatever you want to say, is a stone fence. That's all your property. And you're going to use that stone fence or that stone wall, whatever we would like to call it, to be one of the three sides of your triangle. The next thing that we're going to give you is what you see in red, and it consists of two pieces. I'm going to tell you how long the first piece of the remaining parts of the fence that you need to build. I'm going to tell you exactly how long it is, and I'm going to tell you the angle I want it to make with the stone wall. So I'm kind of setting things up for you. I'm building the first part. We'll call the place where you stop. That'll be just marked point C on our property. And the length we will call little b. So that's a b, not a 6. I'm going to call this point A, as we already said. And so what that means is right here, that angle, that pre-specified angle, is going to be angle A. Now, here's the next piece, and this is the key. We need to connect back to the stone wall. And I'm going to tell you how long your connector piece is. So however we happen to do this, and if you think this triangle piece is going to be opposite angle A, whatever this length, and I call it again the connector, that would be little a in your triangle. And by the way, whatever point you connect back to down here, that ought to be capital B. Just file that away. So one of the first things is we got to figure out, okay, did you give me a big enough piece to connect back? And we're going to find, hey, there's an absolute minimum value that's required. Here's my first possible connector. Hey, we'll use Lego marks. We'll say that as a unit. That's 4 bricks. What do I notice? There's no way I can connect back. I can't make a triangle. My connector isn't long enough. And it turns out, with a little bit of work, what we'll find out is if we happen to have something that's 6 units, 6 little dots, 6 bricks lengths long, it works perfectly. It just touches to the fence. And by the way, we've built a right triangle. So we've seen 2 conditions so far. Connector too short, can't build a triangle. Connector, quote, just long enough, just long enough. Remember, straight line, that's the shortest distance between 2 points. We need to get from C back to here. We ought to have C be perpendicularly connected relative to the stone fence. That's the minimum value that we could work with. Now, suppose our connector is a little bit longer. This one, 1, 2, 3, 4, 5, 6. I got 8 bricks on this yellow piece. Suppose that's how long they gave us. Well, one of the rules is you got to connect directly to the fence and this stone wall. So in order to do that, I could go ahead and fan my connector out to the right, make a pretty big triangle. But here's one of the other things you can probably notice, and do this with a little experimentation of your own, or just visually think. I could also make that connector pull in to the left. And I'd have, it's very, very skinny, but if you look, the white space there, that would represent a triangle. It would represent a nicely done and workable fence for me. So it turns out there's some lengths where I can do what? I have 2 ways to build a triangle. I like to call it, when I fan out this way, I like to call it my go right triangle. When I tuck back in, I get my go left triangle. If I wanted to maximize my area, hey, I'd go this way. If I want to minimize my area, I'd go that way. Different ways to just kind of think through these pieces. Now, I've now seen a no triangle option, a one beautiful right triangle option, 2 options. I can fan out, I can go right, I can go left and build 2 triangles. Now let's look if my connector is really big. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16 units. Well, again, I could fan this puppy out to the right. And one of the assumptions here is my stone wall goes on as far as I want it to do. My property extends way, way out in this direction. Can I fan to the left? The answer is no. How come? Because my connector is much longer than that piece that's already in place. I need to connect what? I can't connect on someone else's property. You can see I've already gone off the video screen or whatever. That's not going to be an acceptable triangle. I can't go past point A. So what do we see? A 2 triangle option where it's big enough to build a triangle, and it also turns out that I can go both left and right. Or, hey, if I get real, real big, gee whiz, I only have 1 option. And I'll only have 1 option if my connector, one other thing to think about, as soon as my connector is bigger than this existing piece, I would have to go to the left of point A. I can't do that. I can only build 1 triangle. So, no triangles, 1 triangle, 2 possibilities, 1 go left, 1 go right. 1 possibility, I have to go to the right. Now there's one more thing I'm going to do. I'm going to superimpose on the next screen the 2 triangles that we built if I went this way or if I went this way. And it would look something like this. If I go to the right, my third part of the triangle is this blue piece. If I go to the left, my third part of the triangle is right here. And that's determining, hey, where is point B? If I go to the right, point B is way out here, far away from A. That part of the fence is pretty long. If I come back, I call this B sub L. This is my go left connection. Gee whiz, what do I notice? Close. And that makes sense. When you tuck this thing back to the left, you're going to be getting closer to point A. But here's one other thing to think about as you look at those 2 triangles. Let's think about angle B in each of these. In my go to the right, fan out to the right triangle, there's angle B. If I decide to go left, there's where angle B happens to live. And take a look at the following. Over here, angle A is what? It's less than 90 degrees. It's an acute angle. If I go over here, what do I know about angle B? It's an obtuse, greater than 90 degree angle. And this 2 option choice, 1 angle acute, 1 angle obtuse, is going to be what we'll work through as we work through some of these example problems with what's called the ambiguous case. When I'm given an angle, that's an angle, I'm given a side, and I'm given one more side, and when I draw this, I kind of create the connector, make it look like that. I don't even know if I have a triangle, but those are the three pieces that I'll define in my triangle. So when I have angle, side, side, I have what's called the ambiguous case. What I can build depends on what this value of A is that I'm given. And we'll work through our examples now. Now going to work through three problems from our notes using the ambiguous case and the law of signs. You can see our pictures up here. Those are nice representations. Connector, not long enough, no triangle. Just right, one solution, which turns out to be a right triangle. Hey, nice view. I can go both left and I can go right. There's two possible triangles I can build. Connector is good enough to work, but it can only go to the right. I can't go to the left. One solution. Lots of different results that we could get. Let's work with our first problem. For ease of time and to save you watching a lot of handwriting, you'll see work filled out as we go. So we're going to start with the problem as given to us. Triangle XYZ with angle X equals side X equals 1.5, angle X equals 30 degrees, side Z equals 2 centimeters. Find the lengths of the other two sides in the third angle. This is a great example of that ambiguous case we have. Angle, two sides. Remember this following piece. When you look for this, look for the same letters. When you see the same letters like this, one angle, two sides, and the letter associated with the side matches the angle, that is the connector. So X equals 1.5 is the connector. So look how I've drawn my triangle. X, down in the lower left, 30-degree angle. Z is my predefined piece, gave it 2, and there's my connector, and I've just drawn it at 1.5 just so I can kind of see it. I don't know where exactly it will go, but I just want to put it out here. I know that this is little z, that length 2. That means point Z is going to be somewhere down along this base. Remember, that's what we call the stone wall that could go on forever and ever. And point Y lives up here. So, what do I know? Well, I don't quite know. I know Z is somewhere along here. I don't know what angle Z is, where it exactly is, but I know the following. I can say the sine of 30 degrees over 1.5 is equal to the sine of angle Z over 2. Angle Z somewhere down here over 2. Angle X, 1.5. Sine of 30 degrees over 1.5. Sine of angle Z over 2. And if I do a little bit of work, what do I come up with? Well, when I do a little bit of simplification, I can say that the sine of angle Z is nothing more than 2 times the sine of 30 over 1.5. And if I run that through the calculator, I'm going to wind up getting 2/3, or if I want to do decimal, 0.667. I now know that the sine of angle Z, wherever it's going to be placed, is equal to 2/3. How can I find out angle Z? Well, here's our statement again. It's my inverse trig functions. I can say that angle Z is equal to the inverse sine of 2/3, or 0.667, whichever you put into your calculator. And when you do that, remember you'll be in degrees mode, you're going to get back 41.8 degrees as an answer. But here's the interesting wrinkle that you need to consider. Remember, there's an angle in quadrant 1 that has a positive sine function. There's an angle in quadrant 2. All students take calculus. Quadrant 1, quadrant 2, the sine function is positive. There's an angle in quadrant 2 that also has a sine equal to 2/3. And if we remember, this is our good old bow tie. There's a quadrant 1 angle. That's a reference angle. Who has 41.8 degrees as its reference angle in quadrant 2? And the answer is 180 minus 41.8, 139.2. So it turns out, hey, we might have two triangles. And if we so do, when I go right, my angle will be 41.8 degrees. It'll live right in there. If I go left, it'll be this cute little angle right there. That's going to be 139.2. Excuse me, 138.2. Please let me correct that. My fault. Bad subtraction there. Okay. So as I work my way through this, what am I going to have? I'll work my way through these different pieces, and what I'll be able to say is the following. I'm going to look with my triangle that goes right that features that 41.8 degree angle. What will I know? I will know that angle X was 30 degrees. I know that 1.5 and 2 were the lengths for X and Z respectively. I know that Z is going to be 41.8 degrees. This is my go right triangle again. How do I solve? Well, if I got two angles, and hey, by the way, I happen to have two sides, 180 minus 30 minus 41.8 gives angle Y, the thing that lives up top in my triangle, it would be 108.2 degrees. And if that's the case, well, I can say the sine of 30 degrees over 1.5, sine of X over X, is equal to the sine of 108.2 Y, sine of angle Y over little y. And if I do my work, I'd say Y is equal to 1.5 times the sine of 108.2 degrees over the sine of 30 degrees. And I'm going to get an answer that's right around 2.85. So there's one triangle. I have this outside triangle. This is the two possible solutions. What I'm going to do next is I'm going to see, hey, will that 138.2 degree, can that support a triangle? It'd be my go left triangle. So over here, what do I have? 30 degrees, 1.5 and 2, those are the things that are already known. I know that Z equals 138.2 degrees, and that tells me if I do a little subtraction, let me fix something here, calculator error. 180 minus 30 minus 138.2 gives me 11.8 degrees for my second piece. I now know all three angles, 30, 139.2, right there is where that 139.2 angle would live, and 11.8. What would be Y in this case? Well, same concept, just like we saw over here, just a slightly different angle. I'm going to have the sine of 30 degrees over 1.5 equals the sine of 11.8 degrees over Y. Y equals 1.5. Let me go ahead and put it into the calculator this time. 1.5 times the sine of 11.8 divided by the sine of 30 degrees. Let's run it. 1.5 sine of 11.8. I'll take that answer. I'm going to divide it by the sine of 30 degrees. And I walk into an answer that's just a little bit bigger than 0.61. So 0.61. Do I have two different possible triangles? In this example, I sure do. I have a fan out to the right, a go right triangle, labeled over here. Y equals, let me put in my 2.85 so I can see the whole triangle solved. Or I can have my go left, again, solved. So here's the case where I had a nice connector and it was flexible enough that it could go to the right or it could go to the left. Okay, two more examples to work through. We're going to work example 4. I'm going to do the same thing. I'm just going to kind of cover up all my structure and then we'll work the problem. We'll start with our diagram again. I have, in this case, triangle QRS, little q equals 20, angle Q equals 30, S, little s equals 16. Again, two sides in an angle. What do I notice? My angle, capital Q, its small counterpart, the length opposite, is also here. That's the connector. And I've drawn the picture. 30-degree angle coming off point Q. I know that point S is somewhere along my good old fence, the border. I know what? Little s is 16. And I know that my connector, little q, is 20. This triangle is drawn pretty well. Can this piece connect back? Now, what you might think about is if you remember a couple things. This connector is bigger than 16 units. I can't bring something bigger than 16 units back to the left. It's going to wind up too far over here. It's going to be off, remember, off my property. I can't have a legitimate fence. But we'll find out. I think I can stretch that way. So let's look at our example again. Here comes our calculation. The sine of 30 degrees over 20 this time. angle Q, little q, is equal to the sine of angle S, which is somewhere down here. Again, I don't know where point S is B on my triangle, but it's somewhere down here, divided by 16. And again, simple algebra, the sine of angle S is 16 times the sine of 30 divided by 20, or equal to 0.4. What do I do next? Same thing, sine of S equals 0.4, find an angle. Get a quadrant 1 angle in this case. Inverse sine of 0.4 gives me 23.6 degrees. But remember, I'm trying to solve sine of S equals 0.4. There's an angle in quadrant 2 that also does that. And that angle is 180 minus 23.6 degrees, or 157.4 degrees. So I'm going to test my go right and my go left. With go right, 23.6. With go left, 157.4 is that second angle, angle S. Now here's what I want you to think about very quickly. I already know that angle Q is 30 degrees. 30 plus 157.4 is 187 degrees. If I was going to try to build this go left triangle, it requires my angle to be this big, angle S. However, if I add that plus the other angle I already know, 30 degrees, I get a value bigger than 180 degrees. I can't have a triangle where the angles add up to more than 180 degrees. And what's that telling us? It's confirming. The math is now confirming our suspicions, what we already kind of knew just by staring at the numbers. I can't build a go left triangle. And that's what you see happening over here. My first two angles in this potential triangle are too big. I can't build a go left triangle. But I can build a go right triangle, and that's what we'll do. What I already know, angle Q was 30, little q 20, little s 16. Angle S came back at 23.6. That's my go right option. And what's that tell me? Angle R, 180 minus 30 minus 23.6 gives me 126.4 degrees. 126.4. How do I find little r? Well, there's my setup. The sine of 30 degrees over 20, angle Q over little q, is equal to the sine of angle R, 126.4 divided by little r. Again, quick math, R is equal to 20 times the sine of 126.4 divided by the sine of 30. 32.2 is what I'll come back with for side R. This is the example, ambiguous case. What did I find out? I can definitely build a triangle. It's the one where what? My connector is really, really long. It's bigger than that first piece that I was given. I have to fan out to the right. I can build one triangle. I can't build two. One more problem to work our way through. It's example 4. JKL. Take a look again. You got angle J. You got side little j. And you have one more side, K in this case. Draw J for sure. 1.4, there's your connector. It goes over here. And you know that K equals 2. Put that on the what? That first piece that they gave you. That means that letter K is buried somewhere down here. Letter L lives up top. What does the law of sines this time tell us? Well, angle K is going to be involved. It's going to tell you that the sine of 45 degrees, sorry, I forgot to mark that. The sine of angle J, 45 degrees over little j, 1.4, is equal to the sine of angle K, wherever it happens to be, over 2. And again, quick cross multiplying, sine of K equals 2 times the sine of 45 over 1.4, and you get 1.01. The sine of K equals 1.01. You need to do work to figure out what? What's the value of angle K? Well, you're going to put it into your calculator. You're going to calculate the inverse sine of 1.01. It comes back as undefined, or you get, a better message, a domain error. And one of the things that we talked about, the sine function, the inverse sine function, its input domain runs from -1 to 1. Those are the only values. Go back and look at your graph in section 5.4 when we talked about that function. There is no angle in the world. That's what a domain error is coming back and telling you. There is no angle in the world that would have a sine equal to 1.01. And if there's no such angle that can do that, you cannot build a triangle. This is the example where your connector is not long enough, and as a result, there's no triangle that you can build. This is a no solution. Connector too short, whatever term you want to use, but you can't solve this one. So that's a good demonstration of the kind of the three main pieces that you will see coming out of the ambiguous case. The only example we did not do would be the case where you have one perfect right triangle. Oops, sorry, as I hit that. That little case. If you did, what you would find out is angle B will come right back to you as 90 degrees. So if you ever do walk into that one, your law of sines will just tell you, hey, that angle B is equal to 90 degrees. So that concludes the lesson. Work through these problems. If you need to, freeze the video and stare through, go back with each of these, just freeze the video, look at the numbers as we've worked them out, and this should give you a good feel for the ambiguous case and how to work your way through it.